No, no, no. That's written as is. So that was.
I didn't know how to get the magnitude because I plotted it. It didn't have to be like 4.
Oh, this is me being exceptionally sneaky on this problem, right? You guys. So we're looking at spring 2012, exam problem 3, where I've given you some MATLAB code, and I asked you to get a reasonably accurate sketch of what's going on. So, and I give you A. So there's sort of like two relevant bits of information. The first bit is A, which is our board's got erased. That's nice. So it's 1.5 minus J times 1.5. There's another crucial bit of information I give you. Any takers?
The e to the j pi over 2.
E to the j pi over 2t. E to the j pi over 2t. Is there any harmonics here? What are the harmonics like? What's the a sub n's? Do you guys have this question in front of you? Or am I the only one that came prepared? There's only one harmonic, right? There's no for loop adding together harmonics. So there's only one frequency. What does that tell you? It's a pure cosine, right? Only one frequency equals pure cosine. What is the frequency of that pure cosine?
You don't know.
Sure do. Pi over 2 radians per second.
Shouldn't that be the phase?
Hold on. That's the frequency. Remember, it's always A e to the j omega t. That's the frequency. And this, the A, tells you the magnitude and the phase. So let's look at what we've got. We've got a cosine. We know it's a cosine because it's only one frequency, right? Only one harmonic. We know the frequency has to be pi over 2 radians per second. Now we got to interpret this A. A tells us how much, like the amplitude and the phase. But in order to interpret this A, we need to convert it from rectangular into polar. Yes, you were going to say? Yeah, exactly. So, right, well that's the magnitude. So the magnitude of A is going to be the square root of the real part squared and the imaginary part squared.
I did that, but when I plotted it, I got 4 as the amplitude, and that's not going to give me 4.
It might.
You got to multiply by 2. Remember, your cosine is A times.
Right, A times twice the amplitude. Right, well let's try that real quick. If we take 1.5 squared plus 1.5 squared, and then take the square root. How do I do that on this? Square root is that sign. I get 2.12. Right? And now my phase angle of A is always going to be the inverse tangent of the imaginary part over the real part, which in this case is the inverse tangent of negative 1.5 over 1.5. So I need the inverse tangent of negative 1. Negative 45 degrees. And because we're engineers now, we're not in high school, instead of 45, we're going to express it as radians. Right, so it'll be minus pi over 4. Okay, so let's put it all together. I got a cosine. What's the amplitude of my cosine? It's got to be double that. Okay, so I need a cosine that's going to go roughly between positive 4.24 and minus 4.24. Because remember, it's always twice the amplitude of A. Okay, it's a cosine. And then what kind of phase shift do I do? To the right. How much is pi over 4? Like, give me an idea. Like, is it just a little shift? Is it a giant shift?
0.75, right?
What's that?
0.75.
0.75 what?
Seconds.
How do you get that? I'm not saying you're wrong. I'm just saying, how do you get it?
Find that out. 3.14 divided by 4.
3.14. Oh, well but this is in units of what? Radians, right? You want to convert it into seconds in order to calculate the shift.
Well, you could also find out how big the period is and then.
Good. There's two ways we can do this, right? And they're equivalent. Step one is, why don't we start by figuring out what the period is here in terms of seconds, right? So to do that, first we convert it to hertz, which is this number divided by 2 pi, right? It's omega over 2 pi, gives me, so that gives me 1/4 of a hertz. And therefore my period is 4 seconds. Good. Now, if my phase shift is minus pi over 4, can I convert that into seconds? Totally. What was, you guys remember the equation for that? Right. If I take that and divide it by omega, I should get the phase shift in terms of seconds. So that's going to give me 1/2 second of phase shift. So my period is 4 seconds, and I'm shifting it to the right by 1/2 second. So not that much, right? So maybe a little bit like this. So from here to here is 4 seconds. And from here to here is 1/2 second. That's reasonably accurate. That's actually very accurate, right? I think we would have accepted something a lot sloppier than that for most of the points. Is everybody cool with how to work for partial credit? You got to throw me a line, right? Me and John are going to be grading your exams. Help me help you, right? Don't just put an answer without any explanation. If the answer is wrong, I can't give you partial credit, right? If you write stuff out, I can be like, oh, I see what he was thinking. Okay. You know, if you get an answer and your answer is clearly wrong, just say, hey, I'm at least smart enough to realize that -4 hertz is not possibly an answer. Okay, that hertz has to be positive. Okay, then I can at least know that you realize your answer is wrong and not like completely throw you under the bus. Help me help you. Cool. That's a good question. I like that question, right? That question really makes sure you knew homework 1 and you understood some of the, actually not homework 1, that's just the code we were working on in class. All right, we've talked about building harmonics into signals. Cool. Anyone else? Should we call it a day? Somebody's got to have another question. Yes.
Do we have like MATLAB code on the test?
Well, yeah, it's possible. I haven't written the test yet, but I'm not ruling it out. But my thing with MATLAB code is I don't really like asking people to write MATLAB code. I've learned that never goes well. But I'll either give you code and say, what's wrong with this? Or I'll give you code and say, what does this do? Or maybe I'll give you a bunch of code and have you add 1 line or something.
For spring of 2011, can we do number 2? It deals with the Fourier transform. I'm not sure if that's going to be on the exam.
Spring, you said, sorry, we said spring 2011?
Yeah.
Problem 2. Sketch the Fourier transform of signal x magnitude only. Let's see. Sketch the Fourier transform of signal y magnitude only. And now we multiply them. Oh, yeah. So I think, didn't we agree that our exam would be Fourier series only, right? We're going to only go through periodic signals. Right. But you should know how to do both of those, though. I mean, those are both, like, you should be in your, you should be able to do that whole problem. Like, what is the Fourier transform of that cosine? Just, like, roughly speaking.
The cosine, isn't it just 2?
Yeah.
It's 3 different.
Not 3.
I think you're reading the wrong problem, Dr.
I'm sorry. Oh, I'm reading the wrong problem?
Are you reading problem 2? Number 2.
Reading problem 2 of spring 2011. Oh, I beg your pardon. Here it is right here. Problem 2, you said? Oh, snap. Look at that one. Find an expression for the Fourier transform. Shown it right. I did that. I'm a piece of work. There's actually a shortcut to getting that that you haven't learned yet that would make that problem a lot easier.
Would you just find the one side and then it's like the inverse of...
You talk about this problem, right?
Yeah.
Is it?
Yeah, the trapezoid one.
Shortcut like Laplace where you use a table or?
No. The shortcut is you find the Fourier transform of its derivative.
Oh, okay.
Where do you find the equation of the lines in this? That's the hard way.
Have fun filling out 4 pages of calculus. That would be the hard way. It'll work. You'll get the same answer, but it will take you about 10 times longer than everyone else. Yes.
All right.
So let's not worry about that one. That's for exam 2.
My question was more about the purely real, purely imaginary.
Oh.
Or needed.
Right, purely real, well, that we can answer. So, we sort of just touched on this very briefly, but there is this property of Fourier series and Fourier transforms, which says that if your signal x of t is even, then the Fourier transform, or the Fourier series, it doesn't matter, is purely real. That means that when you solve for a, like either a sub n, or a sub omega, depending whether you're Fourier series or Fourier transform. You know, that's like a complex number, right? But it's possible some complex numbers have no imaginary part, right? They're either the phase is 0 or the phase is pi. Okay? So if you have an even x of t, your Fourier transform will always be real, purely real.
That's a cosine without any shift, isn't it?
Right, exactly. That's a cosine without any shift. It's either a cosine that looks like this, right? That's a cosine without any shift, because it's an even function, right? So if I'm going to build an even function, I got to build it out of even functions. Okay, so they're either going to have shift like that, or they're going to have, right, be upside down. But that's a phase of 0, and that's a phase of pi. Okay.
Does it always have to be symmetry?
Only if x of t is even, you're going to be building it out of this, which means you're always going to have real Fourier transform. If your x of t is odd, then you're going to have a purely imaginary Fourier transform. Okay? And it's exactly the same argument. It's like if you're going to build an odd signal, then you got to build your odd signal out of either sinusoids, which have a phase shift of 90 degrees, or negative sinusoids, all right, which have a phase shift of minus pi over 2. Right? So e to the j pi over 2 is j, e to the minus j pi over 2 is negative j. So if you have an odd signal, it's going to be purely imaginary. Now some signals are neither even nor odd. Like if you look at the problem 2 from that exam, it's neither even nor odd, right? It's not symmetric about the y-axis, and it's not symmetric around y equals x. It's neither.
So aperiodic function.
And it's aperiodic, but that has nothing to do with it. Right, that periodic or aperiodic doesn't factor into this. So it's neither odd nor even. Therefore, this is going to be complex. Right? It will have real part and imaginary part.
So if that graph was split down 0, or
Yep.
split down the middle at 0, that would be an even function at that point?
Exactly, and then it would be purely real. Yep. Right. In fact, an easier way of solving that, like one method of making that problem easier is, and again, this is all stuff we're going to talk about later in the week, but instead of solving this problem, solve this problem, and then apply the time shift property to basically, when you're done, you add a little phase shift to it to account for the shift in time, and then it's easier that way. But we're going to talk. I don't want to get ahead of myself and waste your review lecture. Yes?
Can we do the 2012 problem 4, please?
2012 spring problem 4. Oh, where you have to match the signals to their Fourier transforms? That's a nasty problem. That's actually a really good problem. I like that. So I've given you 4 square waves in time, and I'm asking you to match them to 4 Fourier, like to 4 frequency plots. Okay. So
You could tell by the width.
the width is a factor because some of them have different widths, right? Some have different widths. Some have different heights. Well, they sort of all have the same height. They all have a height of 2, right? They either go from -1 to 1 or from 0 to 2. So they all have the same height. But it is interesting that one of them goes from 0 to 2. And some of them have different widths. So what about x1? What is his period?
Is it appropriate to use what we learned, I think, last class, to say, like, as t goes to infinity, omega is going to get very, very small?
Uh-huh.
So, obviously, if it has a bigger period, then we have to look on the frequency plots and see we have a whole bunch more frequencies at closer intervals.
Very good.
So some are shifted, so they will have different.
Yeah, then just deduce from that, and then twice the magnitude.
I'm with you. Okay.
And then we can look at the magnitude plots compared to the other two.
Right. So you guys have picked up on all the differences. So if you look at those 4 signals, they differ in the following. One has a different period. One has a different phase shift. And one has a different DC offset. Okay? So let's start with the, first I think I like the period one. One of them has a bigger period than the others, right? That's X3. Okay, so if X3 has a bigger period, what do you think we can expect about its frequency properties? They're more squished together, right? It's built out of lower frequencies. So if you look at your options on the next page, which one of those looks like it has the frequencies mushed together? D. Right, exactly. So great. So X3 maps to D. Okay, that's based off of a frequency argument. Okay, so we're done with X3. What's the next easiest one to get?
S1 because it looks exactly the same as X3 except the period's smaller than X3.
Ah.
Just match the rays together.
That's a good one, right? So the observation is that X1 and X3 look exactly alike except for a difference in period. So that means that we need to look for a plot that looks just like D but stretched out a little bit. So what's a good candidate for that? C, absolutely. So X1 has to go to C.
X4 is just phase shifted from that.
So now we're voting for X. So if we look at the difference between X4 and X1, it's exactly the same plot, but it's phase shifted. So if it's a phase shift, that means we need something with the same magnitude, but a different phase. So what does that leave me with? B. Okay, now, so I guess by process of elimination, X2 has to go to A. But there's a cool thing that we could have seen, that we could have known right away about X2. Right, you guys remember our conversation about DC offset? Right, DC offset is whether it's up or down. Now X1, X3, and X4 are all, they're all like evenly balanced. That means they there's the same amount above the y-axis, above the x-axis as below. So all 3 of those have a DC offset of 0. Okay? But the left-right shift doesn't affect the DC offset. That's right. That's right. And that's for X4. For X4, we selected B, right, which is why the phase is all screwy. But if you look at A is on the magnitude plot of A, it's the only one that's got a dot at A0, at omega equals 0. Right? That's your DC offset. So that's why it's the only one that has a non-zero DC offset. Yes.
I'm ready for the next one.
Okay, well, let's just see. Is there any questions about this? I'm happy to answer them. But this is a nice little problem, right? There's no math, but you got to understand this, right? So that's like my problem right there. I like those kind of problems. I can twist you into pretzels without making you have to do any calculus. Yeah.
For B,
Yeah.
we're looking at P plot, why is it to the right side for positive frequencies where in the negative phase angle, and then when positive for...
Like, why is it for the phase angle for B?
Yeah.
Why is it like negative for positive frequencies and positive for negative frequencies? That really just has to do with that particular problem. Like the only thing you know for sure about phase angle plots is they have to be odd, right? So that if the positive frequencies are negative, you know that the negative frequencies have to have positive. Like it's got to be odd. But other than that, I think it just depends on the particular problem. Yeah, go ahead.
Okay, fall 2011,
Fall 2011.
problem 4,
Problem
B and C.
Problem 4, B and C.
So question A initially asks you to find BC alpha, which is straightforward from what we just talked about.
Right, 0.25.
Yes.
Good.
And then part B, it says estimate the period of the signal.
Great.
But at each frequency, aren't you going to have a different period? So how do you get...
Right, but you want to look at what that plot is showing you. So we're on fall 2011, right?
Yeah.
Fall 2011, problem 4. Right, so there's a whole bunch of harmonics there, right? So if you think about your signal that was made from this, right? It had some base frequency, and then when you go to build that signal out of cosines, you need the first harmonic, the second harmonic, and so on. And you're looking at all the harmonics here. But the signal itself was just made out of, was periodic with some frequency, and that's going to be the frequency of the first harmonic.
Oh, okay.
Right. Now, what makes this a little challenging is that the numbers don't quite line up. So, so the way I would look at this, I would say, look, there's 1, 2, 3. There's roughly, the third harmonic just about comes at 2 radians per second. So maybe the first harmonic is maybe at 2/3 of a radian per second. And then from there you can figure out what the frequency is in hertz, and from there what the period is. But yeah, it basically goes according to the first harmonic. Oh, just because it lined up nicely with one of the hash marks on the plot. Because otherwise I have to look at that first harmonic and try to eyeball it, and it's not really clear, right? Because I didn't put a hash mark there. But I say, oh, well, look, the third one roughly lines up with 2, so I'll just use that to be my measuring post. Okay, and then I said for C, suppose the magnitude and phase plots for some signal y are shown here. Sketch the magnitude and phase plots for 2t y minus 1. We didn't get into that yet.
Oh, we didn't? Okay, so I figured the magnitude plot seems, just if it's 2 times,
It's just double.
the height's going to be
Right.
twice as high, and then the phase shift is, I guess that's where I got lost, is when I went to go draw the phase plot of that, I was like...
Yeah, that's Fourier transform, not Fourier series, and we really haven't spent a lot of time talking about those properties, so you can just hold off on that for now.
Would that be, I guess, positive 90s or negative 93s?
No, it's actually a little bit more complicated. You're adding a time shift of 1 second, which means you're adding a phase shift of minus omega radians per second. So the phase shift is actually a function of, it's just a function of frequency. It's going to be, how do I explain this easily without sucking up an entire class? Basically, your phase angle is going to wind up looking like this. We'll cover it later.
Fair enough.
We'll get there. This is fun. This is easier than a regular lecture. I didn't have to prepare anything. I do have to prepare an exam for Wednesday, though. I'm not psyched about that. I could. I'm not going to. Okay.
Do you know roughly what chapter we're up to in your textbook?
Do I know roughly where we are in the book? I could. We are. Yeah, I think that's roughly correct. Let me have a peek here. Hold on. We are square pulse Fourier transform. Yeah, I would say through 11, maybe. How about that? Yeah, we're finishing like in the 10 to 11 neighborhood. Yes.
2008 fall, number 4.
Number 4. Oh, another matching one. Is that the one you're talking about?
Yes.
Yes. Right. I still regret this question. Even now, I look at this question and think, what was I thinking? Well, okay, so part of the reason this question is tricky is that we're still starting Fourier transform, and two of these are Fourier transform plots. Let's see, what's the easiest way to explain this? Actually, well, okay. Well, I think we can still learn something from this problem, even though it's, I don't think I would ever assign this problem again. But can I do this? Okay, so we're looking at 2008 problem 4.
So we can say that the one with the sums are periodic, right?
Beautiful, right? Right, so basically, so I give you 4 signals, and I say, look, I'm giving you an equation that expresses each of those 4 signals as either a sum or an integral of harmonics. Okay, so absolutely. 2 of your options, option A and option, this is another lesson I learned the hard way. Option little a and option little d are sums of harmonics. Okay, therefore those sums of harmonics have to correspond to periodic signals. Okay, so those have to correspond to, therefore, signal big B and signal capital B and capital C. And the two integrals have to go to the aperiodic signals. Now, for the periodic signals, they differ in terms of a lot of things, like one is a square and one's a sawtooth, but the easiest difference to tell them apart is their period, is it not? What is the period of signal capital B? 1 second. And what about capital C? 4 seconds. Okay, so you've got we said 1 and 4. So if your period is 1, then what's the frequency of your first harmonic? Or your nth harmonic, let's say. 2 pi n, right? It's remember omega is 2 pi f, and f is 1 over t. So you can either say omega equals 2 pi over t, or t equals 2 pi over omega. So if right, so the one with e to the negative j 2 pi n has to be the one with frequency 1 hertz, and the other one was a period of 4, so therefore your nth harmonic is at 2 pi n over 4, or pi n over 2. Okay, so examining your options, it looks like option little a has e to the j 2 pi n, and option little d has e to the j pi n over 2, and that's how you can tell them apart. And all that other nonsense in the summation is just there to scare and intimidate you.
What about
Can we do the aperiodic ones? C does go to A. So one of the things that we're going to learn about probably on Friday is that the Fourier transform of an impulse is just the constant 1. And if you look at option little c, it is literally, all there is in that curly bracket is just a 1. So that has to correspond to A. And that's something that we're going to talk about on Friday. Yeah, I'll explain why.
Just the DC offset harmonic, is that what it would be, or is that?
No, DC offset's the other way, right? If you have a constant in time, right? If you have a constant signal in time, it'll be an impulse in frequency, right? Right. If that's all you have, then you look at the frequency domain, all you've got is a single point. As it turns out, the opposite is also true. And I haven't begun to tell you why this makes sense yet, but if you have an impulse in time, then in the frequency domain, it's constant over all frequencies. So basically, this signal contains all frequencies, right? It contains a little bit at every stinking frequency, and we're going to go into that, but we haven't yet. It's kind of trippy.
That's a Dirac delta function, right?
Dirac delta function, yeah, exactly. You can't actually create one of these except on a piece of paper. Like, there's no such thing as an actual impulse. But we study it because it's got a lot of useful properties, and we can deduce a lot of useful things about signals from it. And also because there are a lot of signals that sort of behave like a impulse function, so it's a handy thing to study, even though you can't actually, like there's no button on your function generator that says impulse, right? You know, it just doesn't work that way. Right. An impulse is infinitely tall and infinitely skinny, but it's got a, if you integrate it, it's got a finite integral. Hmm? Yeah, it's profound. It's cool. All right, let's keep going. We're popping through a lot of these. You know what's interesting about these? We haven't done a whole lot of math so far, right?
No, they're all very intuition.
They're all right. They're all that's. So I tend to. Yeah. No, I mean, I have respect for being able to do the math, and I'll usually put like, I think if you look at this, my trend there's usually like one problem that you can just solve by hammering on the calculus long enough. But then the rest of them I just like to see, do you understand this, or do you just, did you just kind of copy this from somebody else, so far this semester?
This is pretty simple. I didn't actually do this part yet, but I'm just looking at fall 2008, number 5A. It just gives a graph, or appears to be a sine wave, and that says to write the most accurate expression possible. When you say accurate expression, do you just want us to write a sine wave for it, and then just fill in the parameters for omega, blah, blah, blah?
Yep.
Okay.
Yep. Yeah, and part of, and for B, like that semester we were talking about the unit step function, the heaviside whatever step function, and that's where for B, that's where that comes from, but don't worry about it for now.
A, it's going to be a sine, but with a negative pi shift.
Well, you can either write it as a sine, or you can write it as a cosine with a shift of negative pi. Either way, it's the same thing. Yes, sir?
I had a question, but since we're not doing Fourier transforms, it's on
I might answer it.
fall 2011,
Fall.
problem 1.
Fall 2011, 1C. Suppose the signal from part A is repeated again at signal 10 seconds and it's negative 10 seconds. Suppose you call your answer to part A x of omega. Find an expression for the Fourier transform y of t. What was I thinking?
But my question was,
I'm sorry.
if you find the first one, right?
Yeah.
Would you just shift the other one?
Yeah, that's exactly what you do.
Okay.
So you shift and add using the properties.
Yeah, that's exactly what I was looking for.
And so you have to express it by x of omega, right?
Mm-hmm.
Would you just do x of omega minus 10, x of omega
Almost.
minus 10?
What you would do is, there's a property that I think we may have discussed it briefly, and we're going to spend a little more time, probably a week from today, talking about it. And this is why I didn't want to get into that problem over there. Sort of. Look, so, well, we have this property that says, okay, suppose you have x of t, and it has a Fourier transform a of omega. Okay? There's a property that says if you take x of t and apply a phase shift, a time shift to it, then what you get is you still get your original Fourier transform, but you also get a term of e to the minus j omega tau. We looked at that, right, when we did the time shift property in Fourier series. So that's the thing. You get the same thing. You just add a little phase shift to it to account for the shift. Yes?
I got a general question about the Fourier transform. How much is it related to the Laplace transform?
It's a subset of the Laplace transform.
So is it basically just you put j omega instead of s?
Yes, that's exactly it. If you evaluate the Fourier transform, it kind of gets trippy when you think about it. Like, if you think about complex space as having real and imaginary, so this is like the entire complex space. So if so the Laplace transform allows you to talk about frequencies. Like here's some frequency s that's got a real part and an imaginary part. Okay, so the Laplace transform allows you to look at signals in terms of having these phases that are these frequencies that have real and imaginary parts. So that's Laplace. Fourier limits you to being on this axis. So Fourier limits you to cases where the real part is 0 and then your frequency is just equal to complex frequency j omega. So sometimes it's easier to think of things in Fourier space and sometimes in Laplace space. But like once we start talking about signals and systems, like for real, then what happens is like you'll talk about a system and you'll say, oh, well, my system has poles here and here, okay, in the Laplace space. But then when you actually want to talk about like the real response of your circuit, you only consider the effect of these poles on your imaginary axis because that's the only place where you actually have cosines that you can build. So basically one is a subset of the other.
Okay.
Turns out the math is a lot easier when you're just doing Fourier. Like the stuff, you can integrate things a lot easier. It's the math, the integrals for Laplace get ugly quickly. Anyway. So yeah, so all I was looking for that problem was that once you solve for x of omega and then you replicate it 3 times, so basically you'll have your original x of omega, you'll have an x of omega corresponding to a shift of 10, and an x of omega corresponding to a shift of negative 10. And then if you really want to be cool, you can factor out the x of omega. That's all I was looking for in that problem. Since you asked, it's a cool problem.
For problem 2,
Sorry. Well, hold on. He had a question. Was that the same question you were asking about?
I think no.
Okay. Well, let's get him. He's impatient. Then we'll get back to you. Sorry. Which exam? Fall 2011, problem 3. Yes. Suppose x of t is a periodic signal with a period of 5 seconds. Compute the frequency of the 4th harmonic. Give units. Okay. So the period is 5 seconds. Period is 5 seconds. What's the frequency of the nth harmonic? Always 2 pi n over big T, always. So in our case, the frequency of the 4th harmonic is 2 pi times 4 over 5. So that's 8 pi over 5. And if I want units, that's going to be rads per second. 5 points. Okay, for part B. Suppose the Fourier series of x of t is nasty, nasty function. Compute the magnitude and phase of the 4th harmonic. Okay, do you want to do that? Okay, yeah, okay. So I've given you a function. So we need to get a sub 4, right? So I'm just going to start by subbing in a 4 everywhere that I see n. So it's going to be 5 sine 8 pi over 5, right? So let's see. 5 sine 8 pi over 5 over 2j, 2j pi n squared. So 4 pi squared minus 1 over j pi times 4. What kind of sick, twisted jerk would put that on a test? Okay, it's just, let's just clean it up, right? It's not pretty, but I think we can work with it. No, I get a calculator. Seriously, don't make this worse than it has to be. Yeah, calculator. Exam is calculator, open book, open note.
Any book?
Huh?
Any book?
Sure. If your books are stored electronically on your laptop, that's okay. But I don't want you running MATLAB, and I don't want you using the web. Do I have to square the? I'm not squaring the term on the top. Yeah?
We're allowed a protractor or like a roll or something like that?
Yeah, whatever you want.
Sometimes people stare at me weird when I use one.
Whatever you want. I'm cool. I'm down with that. That's fine. Okay, I'm just going to type all this in. 8 pi divided by 5. I'm going to make sure my calculator is in radians. I'm going to hit the sign button. Okay, I'm going to multiply that number by 5. I'm going to divide by 2. Going to divide by 4 squared. Going to divide by pi squared. Okay. And then I'm going to subtract from that pi times 4 reciprocal minus. Sweet. Okay, so I'm getting minus 0.095. So a sub n equals minus 0.095 over j. Anybody else get that?
I got it positive, I got it, yeah, that's it.
0.095 over j.
Yeah, so it's.
Okay, so all I did so far, I just put all this into my calculator. I left out the minus, when I actually punched it in the calculator, I left out the minus j because it was in both denominators, and I just threw it in at the end. So I did 5 sine 8 pi over 5, divided it by 2, divided it by 16, divided it by pi squared. Then I calculated 1 over 4 pi and subtracted that, and that left me with minus 0.095. And if I want to express this as a polar number,
You don't have a magnitude of 0.095.
right, well, first of all, what do I do with the j in the denominator? Right, bring it up to the top. So j in the denominator is the same as positive j in the, right. So it's always, if you bring j upstairs, you can bring it upstairs, you just flip the sign on the numerator. So now I've got 0.095 e to the j pi over 2. Done. There's your a sub 4. And that was just plug and chug. And then in C, write the cosine expression for the fourth harmonic. Now look how easy. Look what you've done. You've already got the frequency. You've already got the a sub n. So the cosine expression for the fourth harmonic is, as always, 2 times the absolute value cosine the frequency of the fourth harmonic plus the phase angle of the fourth harmonic. So plugging and chugging, whatever 2 times 0.095 is. All right, so 0.189. So 0.189 cosine, whatever a pi over 5 is. You can leave it like that. Plus the phase angle, pi over 2. Fun. It's actually not a hard problem, right? It's just mostly that a sub 4 is nasty, right? But it's doable. Guys think you can do this? Just cosines. We got 5 minutes. I got time for one more question.
So no Fourier transform like that?
No Fourier transform.
Are you going to post the solutions for these exams?
Yeah, a little later today.
Are you going to post the final answer or the steps?
No, I think for all of them I have like step-by-step solutions.
How do we prove God again?
I'm sorry?
How do we prove God again?
Prove God? E to the j. Yeah, I won't be asking you to do that on the exam.
Nobody was asking anything important.
So I mean, you should. It's a really interesting story. Like you should. People used to, during the Enlightenment, I think people used to argue about this stuff, like, whether or not some of this stuff would add up, but e to the j pi plus 1 equals 0. Like, that could not come from a random universe, right? You've got e, which is the exponential rate of growth in like any biological system. You've got j, square root of negative 1. You've got pi, ratio of a circle's circumference to its diameter. 1, you add them together and you get nothing. It's like, how could that be random? There's, I think it was Descartes. I think I put it in a footnote in the book, maybe.
There's a joke about how many electrician does it take to change a light bulb.
Yeah.
That must have been on Wikipedia, because I read that.
It's an old story. Like I think I read it on Wikipedia when I was trying to confirm it for the book. But yeah, I think here we go. Answers.yahoo.com. Yeah, it was Newton. Okay. No, Euler. I beg your pardon. Anyway, I'll see if I can find like a more primary source than Wikipedia and post it to the website. It's cool though, right? I mean, great minds used to worry about stuff like this.
So real problems came along which they could solve.
How would you get a periodic function? How would you get this transform? Fourier transform as a periodic function?
When we have a periodic function, we think about it in terms of Fourier series.
There was a question that said find periodic Fourier transform.
I may have just been sloppy with my wording.
Okay.
A Fourier, if I give you a periodic signal and say like, what's the Fourier whatever, I'm just talking like you're just going to get a bunch of harmonics, so you have to solve for those harmonics.
For 11, problem 2.
For fall 11, problem 2.
It says sketch the Fourier transform of signal x of t, which is periodic, but there's also a function y of t, which is aperiodic.
Right. Basically, when I say Fourier, what I mean is just get the frequency content. Right. So for the cosine, it's just going to be, for the cosine, it's just going to be, right, just the principal harmonics. And for the other one, the rectangle pulse, we know from class it's going to look roughly like that. And that's it.
So with a periodic function, the frequency content is a discrete function, basically?
Yes, right, absolutely. For a periodic function, the frequency content is always discrete. It's only at harmonic frequencies.
So do you think we should remember like random or this kind of functions, their graph?
You should definitely know this.
Okay.
If I show you, here's a good one. Here's a great one.
1 with 4.
If I show you
With an outside.
crap, hold on. If I show you that, I say plot the cosine. That's a nice problem. 6 cosine 2t plus pi over 3. That's half the battle. Then you actually have to know how that plots. I'm sorry? Well, half the battle is getting this. The other half of the battle is knowing what that looks like when you plot it.
So if you had
Oh,
Well, yeah, it's a cosine, but you have to get the period, you have to get the period, you have to get the phase shift.
So if you had like 1,000 of them, right? If you had so many sticks, would you just look at the first one and say that's your period times n? Or that's your frequency?
If you had a whole bunch of those sticks, the first one would tell you the frequency of the overall signal.
And then you multiply by n, right?
No.
Or no, you don't.
No, not by n. If you had a whole bunch of them, right, you'd be summing together all those different cosines. It would be this cosine plus this cosine plus this cosine. But the overall signal would have a frequency dictated by the first harmonic.
Okay.
Okay, I have another class to teach.